Welcome to another lesson of Math 0420 Introductory Algebra. In this video, we will be discussing Section 4.1, Solving Systems of Linear Equations by Graphing. In this section, we will decide whether an ordered pair is a solution of a linear system. We will solve systems of linear equations by graphing. We will use graphing to identify systems with no solution or infinitely many solutions. And we will use graphs of linear systems to solve problems. Let's start off with an example. Definition. Equations of the form ax plus by equals c are straight lines when graphed. Two such equations are called a system of linear equations. One more definition. A solution to a system of linear equations in two variables is an ordered pair that satisfies both equations in the system. Okay, so we have system of linear equations and solution to a system of linear equations. Example 1. We want to consider the system that has two equations, 2x minus 3y equals negative 4, and 2x plus y equals 4. First, we want to determine if each ordered pair is a solution of the system. Now, we're going to start out with a single pair in part A, and we want to see if the point 1, 2 is a solution. So the way we do that is to plug the point 1, 2 into both equations. Okay, so in our first equation, we have 2x minus 3y equals negative 4, so we'll plug in the point 1, 2, so 1 for x and 2 for y. 2 times 1 is 2, minus 3 times 2 is 6, so that's 2 minus 6, which is negative 4. So that works. That is a solution for that equation. And then we'll plug into the second equation, which is 2 times x plus 1 times y, and y is 2. And we get 2 plus 2, which is 4. Since that point is a point that is true in both equations, we know that that point is a solution to the system. So 1, 2 is a solution to both equations, and is thus a solution to the system. Okay, let's try another point and check to see if it's a solution. The point 7, 6. So again, we're going to follow the same pathway. We're going to plug in 7 for x and 6 for y. 2 times 7 is 14, and negative 3 times 6 is 18. So 14 minus 18 is negative 4. So it checks out on that one. Let's plug into the second equation. So we'll have 2 times 7 plus y, which is 6. 2 times 7 is 14 plus 6. 14 plus 6 is 20. And what should it be? Well, it's not equal to 4. So 7, 6 is not a solution to that equation. Not a solution to the second equation. And therefore is not a solution to the system. So it worked on the first one and not the second. So it's not a solution to the system. It has to work in every equation in the system for it to be a solution to the system. Now this is sort of foreshadowing. We found a solution in part A but not in part B. We'll find out later why we can only have one solution to a set of two linear equations. Let's now talk about solving systems of linear equations in two variables x and y. Solving systems of two linear equations in two variables x and y by graphing. Here are the steps. The first step is to graph the first equation. Your second step is to graph the second equation. If the lines cross in the third step at a single point, we want to determine the coordinates of the intersection. And finally, we want to check that the solution works in both the first and second equations. Let's do an example now where we graph a system of linear equations and try and find. Okay, example 2, we want to solve the system by graphing. We have the system 2x plus y equals 6 and the system 2x minus y equals negative 2. So the first thing we want to do is we want to solve each equation for y. And the reason we want to do that is to get it into slope-intercept form. So starting with 2x plus y equals 6, we can solve for y by subtracting 2x from both sides, and we get y equals negative 2x plus 6. And then, there's our first equation. And then our second, we have 2x minus y equals negative 2. We can subtract 2x from both sides, and we get negative y equals negative 2x minus 2. Divide both sides by negative 1, and we get y equals 2x plus 2. Okay. And we can graph both of those equations now that we know the slope and y-intercept. So the first equation is negative 2x plus 6. So our y-intercept is 6, and our rise is negative 2 for every 1. So we can go down to, let's see here, we can go down to and over 1 to get our second point right here. And then we can use our straight edge to graph that equation. Let's see if that's a little better. Okay, and then we can draw arrows for both. Our second equation is y equals 2x plus 2. Our intercept there is 2. And then our rise is up 2 over 1. And so our purple dot goes right there. Again, we can use our straight edge. I think probably at this point you can see where this is headed. We can draw arrows for both, and then you can see that we have a solution. Both of those lines cross at the point 1, 4. So that is our solution to the system. Now let's check and make sure that it works in both cases. Okay, so we can, in the first equation, it's negative 2 times 1 plus 6, which is negative 2 plus 6, which is 4. So that works. In our second equation, we have y equals 2 times x, which is 1 plus 2. 2 times 1 is 2 plus 2, which gives us 4. So that checks out. So the point 1, 4 is a solution for both equations. And is therefore a solution to the system. Okay, example 3. We want to solve by graphing the system y equals negative x plus 6 and y equals 3x minus 6. So we'll start with graphing y equals negative x plus 6 in green. Now notice we don't have to solve for y in this case because both equations are already in y-intercept or slope-intercept form, so y equals mx plus b. So our slope is negative 1 for the first equation, and our y-intercept is 6. So our rise is negative 1, and our run is 1. So our second point can go there. Pull up our straight edge, and we can draw a straight line through those 2 points. Okay, so there's our first equation. Our second equation we can graph in purple. So y equals 3x minus 6. Again, our slope is 3, and our y-intercept is negative 6. So our intercept point is there. And so our rise is 3, 1, 2, 3, and our run is 1. And so we can give our second point right there. And now we can use the straight edge and go through those points. And let's see if we can draw a straight line through there. Now, do we have a solution? Well, our graphs cross there at the point 3, 3. So that is our solution. Let's check to see if the point 3, 3 works. So our first equation is y equals negative 3, so the negative of x, plus 6. Well, negative 3 plus 6 is 3, so that works out. And our second equation is y equals 3x, so 3 times 3 minus 6. Well, 3 times 3 is 9, minus 6 gives us 3, so that checks out. Therefore, the point 3, 3 is a solution to the system. Let's go back now to a chart and talk about the types and number of solutions we can have for a system. Okay, chart time. The number of solutions to a system of 2 linear equations can be broken into 3 different cases. So we have the number of solutions and what it means graphically. You can pause the video at any time to copy down this chart if you need to. So you can have exactly 1 ordered pair of solutions, and what that means graphically is that the lines will intersect at exactly 1 point. Number of solutions. If there are no solutions, then the lines won't ever cross and the 2 lines will be parallel. And if there are infinitely many solutions, the two lines will be identical graphically. The one that we're usually most interested in is the one where we have exactly one ordered pair solution. Okay, let's try and do example 4. We want to solve by graphing the system where y equals 3x minus 2 and y equals 3x plus 1 are our equations. Okay, so we'll first graph y equals 3x minus 2 in green. Okay, notice our y-intercept is -2. So there's that point. And then our rise and run, our rise is 3, so up 1, 2, 3. Our run is 1. So we have that point. We can then graph using our straight edge. And then y equals 3x plus 1, we will graph that in red. Okay, our y-intercept is 1. And again, we go up 3 and over 1. Use our straight edge to get the full line. And what do we find about these? Well, let's try that again. Didn't quite go through both points. That's a little better. Well, the lines don't cross. So what we find is that there are no solutions because the lines are parallel. They have the same slope, but different y-intercepts. The solution set is the empty set. Or the symbol for the empty set. Okay? Okay, for example 5, we want to solve by graphing the system of equations. First equation is x plus y equals 3, and the second equation is 2x plus 2y equals 6. Both of these equations are not in slope-intercept form, so we will put them in slope-intercept form. X plus y equals 3. To get y by itself, we can subtract x from both sides, and we get y equals negative x plus 3. We can graph this one in pink. So our y-intercept is 3, and our rise and run, our rise is -1, and our run is 1. So there's our point. Use our straight edge to go through both points. Okay, and our second equation, 2x plus 2y equals 6. We can subtract 2x from both sides, and we get 2y is equal to negative 2x plus 6. We can divide both sides by 2, and you get y equals negative 2 over 2, which is -1, so negative x, and 6 divided by 2 is plus 3. Now notice these are the same equation. We'll graph this with a red dot. We would graph it the same way, but the equations are the same. So we're just having those overlap. There are infinitely many solutions. And that's true because these lines, try that again, are identical. Again, you may not have noticed that they were the same from starting out because they don't look the same, but once we get them down to slope-intercept form, they are the same equations. Okay, example number 6. The toll to a bridge costs $2. If you use the bridge X times in a month, the monthly cost is the equation Y equals 2X. With a $10 discount pass, the toll is reduced to $1 per crossing. The monthly cost Y of using the bridge X times in a month with the discount pass is modeled by the equation Y equals X plus 10. So we want to do two things. We want to solve by graphing, and we want to interpret the coordinates of the solution in practical terms. Okay, so our system of equations, let's try that again, is Y equals 2X and Y equals X plus 10. Okay, we'll graph the first equation in red and the second equation in purple. Now, something I want to note as we go to graph this, note that the scale on the y-axis is by 2s and the scale on the x-axis is by 1s. Okay, so in red, 2x is the equation. There is no y-intercept, it's 0. And our rise is 2 for every 1. So that would be our there we go. And then our second equation in purple, notice that our y-intercept there is 10, and we will go up 1 and over 1. So since the scale is 2, we have to go up 2 and over 2, so it's not quite as steep. We have that point. We can use our straight edge there to, we can go through here with our line. First question we need to ask is, do we have a solution? And it looks like we do, and it looks like it happens at the point 10, 20. We can go and check that now. So y equals 2 times 10. Well, 2 times 10 is 20, so it checks out in the first equation. The second equation is y equals x plus 10, or 10 plus 10, which is 20. So it checks out in both equations. So 10, 20 is the solution. So that's part A. For part B, we want to interpret the solution in practical terms. So until the 10th bridge crossing, it is more expensive with the discount pass, but after the 10th crossing, the cost is less with the discount pass. So in other words, not having the pass is good if you are only planning to cross 10 or less times in a month. But if you're going to cross every day, so if you were going to cross 30 times a month or you were going to cross it twice a day every month, then it would be cheaper to go with the discount pass. That is the end of section 4.1, solving systems of linear equations by graphing. Please let me know if you have any questions as you go through your homework. Good luck on that.